Welcome to the video key for quiz 2. So in the first question, we're looking at a phase diagram. So we can see we've got pressure and temperature on the y and x axis, and of course at high pressures and low temperatures, we're going to have a solid. So we've got solid. We've got solid over here. If we go to high enough temperature, we're eventually going to get gas. And in between we have liquid. Okay, so we've got our phase diagram, and the question is, what is closest to the normal boiling point for this substance? So we know boiling is when we're going from liquid to gas, and we're going from liquid to gas anywhere along this curve, but the normal boiling point is where that curve intersects 1 atmosphere, because at 1 atmosphere, if we get the water vapor produced by the phase transition to be at 1 atmosphere, it's going to be able to push back the atmosphere, and so we'll have boiling. And so let's draw a horizontal line at 1 atmosphere. So we're going to go across over here. And we can see that that is closest to 275. It's a little higher, probably more like 280, maybe 278 or something, but we'll use that number if we have to round. And indeed, we do have to round on our answer here. We can see that the closest is going to be 275. So that is going to be our answer. So let's go ahead and circle that. 275 is our normal boiling point. And if we look at where this line intersects the solid liquid line, we can see that's going to be our melting point. That's going to be around 250 kelvins. Number 2, what's the sign for delta H of vaporization? And it doesn't say what substance, but for any substance, the answer is going to be the same. So what is delta H of vaporization? We're going from solid, delta H of vaporization, not fusion, so that's not right. Let me erase that. So we're going from, vaporization is we're going from liquid to gas. And the little circle there means that we've got pure substances at 1 atmosphere. So that's standard conditions is 1 atmosphere pressure. So if we're going from solid to liquid, that means we're going to be breaking IMFs. So if you're breaking IMFs, that's going to cost you energy. So whether you break a full-on covalent bond or ionic bond or just an IMF, that's going to cost you energy. Whether it's an IMF or a covalent bond, breaking bonds or IMFs costs you energy. So we have to put energy into the system. So that means that delta H is a positive number. We're putting energy in. So this is going to be a positive number. So for water, for instance, this would be a positive 40 kilojoules per mole roughly. For some hydrocarbons, small hydrocarbons, it tends to be around 30. It's smaller because the IMFs are weaker. If we have a really long molecule, on the other hand, that has lots of atoms in it, it might be bigger than the one for water. But in any case, we have to put in IMFs. We have to put in energy to break IMFs. Okay, what is the sign for the heat of solution? So heat of solution, so line here, is going to be going from salts in the solid phase to salts that are aqueous. And we're trying to find out what delta H is for this. So to do this process, we have to break a salt apart. We're going to break ion-ion interactions. That costs us energy. But then those ions are going to interact with water. And that's going to be an ion-dipole interaction, multiple ion-dipole interactions, and that's going to release energy. So we have an energy cost, right? Because we're going to break that, and then we're going to have an energy release, which is going to be a benefit. So it's cost benefit, and we don't know the sizes. We can dramatize this a little bit by just showing you that we can go from the solid phase. That's supposed to be an S. I'll make that a little more clear that that is an S, to the gas phase. And really, I don't like this notation. I'm going to go ahead and replace this with individual ions just to emphasize we're talking about ions that are separated from one another in the gas phase. And you might recognize this reaction. This reaction is the process that has the enthalpy that we call the lattice enthalpy. Okay, that's got a positive number, right? Because we're breaking ion-ion interactions. On the other hand, if we take those ions that are in the gas phase and separated and then plunge them into water to get aqueous ions, now we're making ion-dipole interactions. That's delta H of hydration. That's going to be a negative number because we're making ion-dipole interactions in this second reaction. And you might notice that if we add these two reactions up, the lattice reaction and the hydration reaction, we're going to end up, the net is that the gas phase is going to cancel out and we end up with solid going to aqueous, right? So we're adding up one that's always positive and one that's always negative. So without knowing the sizes, we can't say what the sign is for delta H of solution. And so since we can't know whether it's positive or negative without looking at numbers, the answer is it varies. Some salts give off heat when they dissolve. Some salts absorb heat when they dissolve. And you saw this in the lab, right? That potassium iodide, when you dissolve it in the water got cold. So the reaction had to steal heat from the water to dissolve. So delta H was positive. On the other hand, when you dissolve calcium chloride, the water got hot. So the water absorbed heat from the reaction. The reaction gave off heat. Delta H was negative. So some positive, some negative. Okay. All right, what's the sign of delta H of lattice? We already talked about that. When you break up the crystal lattice to form gas, which is what the lattice reaction is, you got to put energy, so it's positive. What about delta S of solution? And this is kind of the same thing. So actually, I'll answer this hydration one down here first. So delta S of hydration, we got to write the hydration reaction, right? We've got ions in the gas phase. I'll just use sodium chloride again. It will be the same. This is going to be the same answer for any salt. We're taking these and plunging them into water to make aqueous ions. And when you do that, we're going to be building up ion-dipole interactions, right? We're going to be taking water molecules that we're able to just flip around at will, and now we're going to be pointing them in a specific direction around each ion. So if it's a positive ion, the oxygen is going to point towards that positive ion. If it's a negative ion, it's going to be the reverse with the hydrogens pointing. So we're building up these ion-dipole interactions. And because of that, the ions have less mobility. So for both of those reasons, delta S of hydration is going to be a negative number. It is less than 0. If we take the delta H of hydration reaction, so I'll just rewrite that. Let's see if I can just copy that. There's no easy. I'll just rewrite it. So if you write the hydration reaction, so the ions in the gas phase going down to form ions in the aqueous phase, and we combine it with the lattice. I want to do entropy, not enthalpy, so let's get rid of those H's. So now let's look at the lattice reaction, where we're going from the salt to ions in the gas phase. So clearly here, you're getting more mobility and some more microstates. So we expect this to be a positive number. So here, we've got this one is a negative number, as we explained below. This one's a positive number. So if we add those up, if we add these two things up, it's going to be the entropy change of solution, right? Because you can see that the gas phase portion is going to cancel out, right? We cancel that with that, and so we're left with solid going to aqueous, which is the delta S of solution. So since we're adding a positive number to a negative number, we really can't say. So we can say here that delta S for solution is going to equal, well, who knows, right? We can't predict. So it varies. So the most common misconception here is to say that when you dissolve a salt, the entropy goes up. If we look up actual numbers for this, we can see that half the time it doesn't, it goes down. So it depends on the individual salt. All right, we mix ice that's at -20 with water that is at 15. Which parameters do we need? So a useful tool here is to draw out the temperature Q diagram. And then we're not going to use the whole thing. And so which parts of it you use tells you how many terms you need. So we started off, and let's label these pieces, right? We've got solid. As you heat it up, as you put heat into it, the temperature goes up. So what do we have here? Here we have melting. And then, so we've got solid plus liquid here. Then eventually you run out of solid and you've just got liquid, so the liquid heats up, so your temperature goes up. But then it stops when you get to the boiling temperature. So we have liquid, but now we have liquid plus gas. And so you have more and more and more gas. When the last bit of solid disappears, the temperature starts to rise again, and now you're just heating up gas. Okay, so you label it first, and then you say, where did I start? Okay, I start off, the ice is at -20, so it's down here. So notice, let me use a different color. Well, notice it's sort of midpoint on this curve, right? We're below the melting temperature. The water was at 15, so it's above the melting temperature, okay? Now, because those temperatures are different, we're going to have heat transfer, right? Heat's going to flow from the high temperature substance to the low temperature substance. So if there's heat flow, this is going to cool off, and this is going to heat up. Now, what we don't know is whether we have more ice or water, right? If we have a lot of ice and a little bit of water, it could be that all the water cools down and even some of it freezes, okay? On the other hand, if we have a lot of water and a little bit of ice, all the ice will melt. And what might happen is that this ice melts, or it heats up, and then it starts to melt, and then it heats up a little bit. So we don't know where on this curve we're going to meet without knowing what the masses are. But we can say what terms we need, because by looking at this, we can see that the ice is at least going to heat up a little bit, right? So we know we need the specific heat of ice, so we better circle that. We know the water is going to cool down a little bit too, so we need the specific heat of water. And what's going to happen is, depending upon the relative amounts of substance, either we're going to end up freezing some of the water, or we're going to end up melting some of the ice. So either way, we're going to need the heat of fusion. We want to have a delta G of solution to be negative. We want this to be a negative, delta G standard to be negative for solution. And notice that's made up of two pieces. And we saw earlier that we can't predict the sign of either of these, but we can predict trends in the entropy of solution with charge density. We saw that water molecules get lined up, they get oriented by ions that are charged. Or I guess ions are charged. They get oriented by ions. Well, they're going to get oriented more the more charge dense those ions are. So that means if we increase charge density, actually we'll just write this down here because these questions are related. If charge density goes up, the water orientation goes up. Nearby waters are going to be pointed at those ions more than they would be if the charge density was low. That means the microstates for the water goes down, which means the entropy of the water and we're talking about liquid water, of course, goes down. So what is that going to do to delta S of solution? It's going to make delta S of solution, we could say that it makes it less positive. So if it's a positive number, it becomes less positive. In other words, putting ions in the solution generates less entropy than you expect. It could even make it negative. So you can say more negative. Okay, these are the same things. It's going to make it move down on the number line. Okay, so less positive, more negative, delta S of solution. So if higher charge density is going to make the entropy change less favorable, we want to have the entropy change become more favorable, so that would be low charge density. So if we have a salt with low charge density, or ions, it's made up of ions with low charge density, in general, that's going to make the entropy change more favorable. It's going to have a more positive / less negative delta S of solution. So that would lead to greater solubility of salt. Suppose we mix water that is at 20 degrees with water vapor that's 100 degrees. What parameters do we need? So we go back, we draw that same diagram again. So we've got temperature and heat. We have all the different possible forms of water on our diagram. So we've got solid, liquid, gas, and then we say, what do we have? We have water vapor. Let's go ahead and label these parts too. Temperature boiling and temperature boiling is up here, temperature melting is down here. Okay, we had water at 20 degrees, so we're above the melting point, so we're here. And we have water vapor at 100 degrees C. So notice we have to be at the bottom here. We have to be at the boiling point. Now notice, let's label these other pieces. We've got liquid plus gas, and we've got solid plus liquid. That if liquid and gas are in equilibrium, if we're on this line, we can't budge from 100 degrees. Okay, we can't budge from 100 degrees until we get rid of the last bit of liquid. Same thing down here. You can't budge from 0 degrees if we're talking about water, as long as you have any solid or any liquid. And as soon as you get rid of the last bit of solid, then we can start heating up our liquid. Okay, these are two different temperatures. So we know that this is going to start heating up. And this is not going to cool down, but it's not going to cool down in terms of temperature change, but it's going to lose heat, right? It's at 100 degrees, the other one's at 20, so it's going to lose heat. But heat is not going to go into, the loss of heat is not going to cause a temperature decrease, it's going to cause the water vapor to condense. So we've got this term, and where these arrows meet is a function of the relative masses of water vapor and water. But all we know is we're going to have both of these terms. Right, we're going to have an MCAT term over here, and we're going to have an N delta H of vaporization over here. And this is C for liquid water, right? So we do need the specific heat of water, we do need the heat of vaporization, but we don't need the specific heat of water vapor, right? We don't need that. Why? Because we're already down at 100 degrees. We can't cool water vapor below 100 degrees. As soon as we try, instead of cooling down in temperature, it just condenses. Okay? All right, and that was the last question. So thank you for watching, and see you in class.